Good day, ladies and gentlemen. You are welcome to our lecture number 2 on Mcen508 Power Electronics and Drives. This is our lecture number 2. I am Kabir Ahmad Abu Bilal. In our first lecture, we have seen the general revision on the course, and of course, we looked at the 6 basic switches that are used in power electronics. And the first one of them is a power diode. So today we are going to continue our lecture by starting looking at each of these 6 components or switches. The first one is a power diode, and the power diode, as we know, they are mainly made of silicon. Sometimes they are made of germanium, and they are PN junction. They have 2 terminals, as everybody is supposed to know from 200 level and 3. That is, we have cathodes and the anodes. And this PN junction diode is formed. If you want to produce it, you need to remember your basic semiconductor. You know that in semiconductors we have what we call the pure, that is intrinsic semiconductors, and we have extrinsic semiconductors. So the extrinsic, they are of 2 types. We have the N type and we have the P type. Okay, so the diode is formed by combining 2 of this, that is one P type and the other one N type together. So that is why we call it PN junction diode. And the processes of producing the PN junction are 3. We have allowing methods, we have diffusion methods, and of course there is what we call epitaxial growth methods. The allowing method, as the name implies, is a method where we produce PN junction diode by combining metal. Basically, the metal used in this case, as we are going to see under Schottky diode, is the aluminum together with the common semiconductor, that is the N type. Excuse me. Then the diffusion process is a process where if you have a pure silicon, you now inject the group pipe element in one side through the diffusion. We know the diffusion is a process of transfer of substance from the region of higher concentration to the region of lower concentration. So we diffuse the group pipe element into the pure silicon on one side and diffuse the group 3 element on the other side. Then on one side we have P-type material, and the other side we have N-type material. And the epitaxial process or growth process is a process where you grow one layer of N-type, maybe on top of it you grow the other layer, which is P-type. So the power diode, as we have seen, is one of the basic components which are used in this semiconductor power electronics. It is used in this semiconductor power electronics, and the advantages it has whenever it is used in these areas include it has high mechanical and thermal reliability, and it has high peak inverse voltage, that is the reverse voltage that can damage it is very high. Then it has low reverse current, that is to say the leakage current is very small, which minimizes the losses. And it has another advantage of low forward voltage drop, that is whenever it is conducting normally in forward bias, the voltage drop, which is a source of loss, is very small. And for this reason it has high efficiency, and of course it has an advantage of compactness, that is, it is very compact, it is not bulky, it is very small in such a way that it can be used without much trouble. Now let us look at the biasing of the diodes. The diodes can be biased either in forward or in reverse mode. The diode is said to be forward bias. It's said to be forward bias when the anode is made positive with respect to the cathode. Look at the diode. This is my anode and this is my cathode. I connect the positive terminal to the anode while the negative to the cathode. In this case, we say the diode is forward bias. While when the anode is made negative with respect to cathode, then we say this one is reverse bias. And this is the characteristic curve that shows the conduction when it operates in forward mode and in reverse mode. The diodes normally they are made using either silicon or germanium. They are made using either silicon or germanium. Okay, so if you have the diode which is made using silicon, there is a minimum forward voltage that will make it to start conducting, and that is what we call the cut-in voltage or turn-on voltage. Okay, the silicon diode required 0.7 volts for it to be forward biased, and for the germanium it requires around 0.2 to be forward biased. So in this curve, as you can see, when that of silicon, let's assume it is the T1, reach minimum value of that 0.7, the current will start rising exponentially. For the germanium T2, when it reaches 0.2, it will start rising exponentially. That is in the forward bias mode. But when it is reverse bias, ideally the diode is unidirectional, meaning it conducts only in one direction. That is when it is forward bias, it is on. When it is reverse bias, it's supposed to be off. But nevertheless, because of the existence of what we call minority charge carriers, we do have some small amount of current that flows even when it is reverse bias, and we call that one reverse leakage current. And when you keep on increasing the reverse voltage, you reach a damaging point. We call it avalanche breakdown point. That is where the current will start also rising in the negative direction exponentially, which means the diode is no longer good, it has been damaged. That is the static characteristic of a diode, where we don't take time into consideration. Then we have a dynamic characteristic of a diode, and this dynamic characteristic, whenever we are operating at low frequency, the low frequency they range it anything from 1 to 1 kilohertz. You find that the diode is just assumed to be a perfect switch. Therefore, the dynamic characteristic is not important because it is not affected by the frequency because it is very low. But whenever the frequency starts rising above that minimum 1 kilohertz, you find that the high currents, the dynamic characteristics are very, very important. And the reason why we have to consider the dynamic characteristic at high frequency is because it increases the power loss, and it also gives rise to what we call the voltage spikes. This voltage spike is just a surge, that is sudden increase in the voltage that can cause damage to the device, except if you give a proper protection to the diode. And for us to understand the dynamic characteristics, let us look at the simple power diode diagram. This is the diode which is supplied by this voltage, and this is our RL, which is the load that will be absorbing the output of the diode. Let's assume this is my input waveform, and it is digital in nature. It is either high or low. When it is high, you find that we have a concentration of charges in the diode due to the majority carriers and the minority carriers at the same time. So when the diode finally suddenly switched to low, you find that the charge will never go back to zero, but rather it will start decaying gradually before it crosses the zero line, and finally it will maintain a constant negative value. And the reason why it doesn't change suddenly to zero is because we have minority charge carriers in the depletion region, and that is the reason why this has to be taken time gradually to be recombining with one another before it finally reduces to zero. And even after that, we still have a residual which gives us that small gap here. And here is the current. Whenever the voltage, the waveform input is positive, that is high, you find that the current is also going to maintain that high value. When it suddenly drops to negative, the current will also change, but when it take a very small time, it will now start increasing because of that small minority charge carriers we talked about, until it reach a point where we maintain a very small amount of current, and that current is what we call the reverse leakage current or the reverse saturation current. And this is the waveform of the voltage. When the input is high, the voltage is high also. When the voltage suddenly drops to low, you find that the voltage reduces. It is positive, but it will reduce because of this residual charge carriers I talked about. After crossing the line 0, then the voltage will start decreasing until it reaches the maximum negative, just like the waveform here, and it will continue like that. Now, there is what we call the reverse recovery characteristic of a diode. Whenever a diode is forward biased, okay, when the diode is forward biased, this is the characteristic I have just discussed, okay. But when the reverse recovery characteristic is more important when we are talking of the reverse operation of the diode, not in the forward bias mode. And the reason why the reverse recovery is very important than the forward recovery is because it increases the losses which will be added to the forward loss. Okay, so this current of the diode, when it is forward bias, we know the current that we get is as a result of the combination of majority carriers and the minority carriers at the same time. Okay, but when the diode which is previously forward bias is now reverse bias, the current will start approaching 0 as I have shown on that diagram, and the diode will now continue to conduct a very small amount of current, and I told you is because of the existence of these minority charge carriers which exist at the PN junction, not in the actual body of the material, but the ones in the depletion region where the two P and the N meet together. These minority charge carriers will take some time before they recombine with one another, thereby neutralizing each other, and finally when they recombine completely, they will become 0, and that is when we expect to have no more current because the charge carriers that produce the current have recombined and disappeared. Now, there is a time that we call the reverse recovery time, and that is the time it will take for these minority charge carriers to recombine with one another so that they can disappear. So the time taken to do that is called the reverse recovery time. And this reverse recovery time, if you want to determine it, is to, let us look at this waveform. You will find that when the diode is forward biased, the current is at its high value. The moment you switch it to the reverse bias, the current will start decreasing gradually. I have already explained this. The reason why it never go back to 0 instantly is because of the existence of those charge concentration at the junction. So when you reach the 0 line, so the time it will take from that 0 line to the peak value of that reverse recovery current is what we call T1, and from that it will now start rising up until it reaches the 25% of that maximum value. So the time T2 is between when it is at peak and when it now rises to 25% of the maximum. So if you add these two times, that's T1 and T2, it will give you the reverse recovery time. Okay, and there is a current that is conducted in that reverse recovery phenomenon, and we call it reverse recovery current, I subscript RR. And to calculate that current, we use this formula: T1, that's the time from 0 to the peak, times the rate of change of the current, that is di dt. Now, this reverse recovery time depends on some 3 factors. The first one is the junction temperature. The higher the temperature, the higher the time for that reverse recovery. And the second one is the rate of fall of the forward current. The more the rate of falling of the forward current, the lesser the time for the reverse recovery. And the last one is the magnitude of the forward current prior to the commutation, that is prior to turning off the power diode. When the magnitude is high, the reverse recovery time will also be high, and vice versa. Okay, normally this forward recovery time is less than the reverse recovery time. That's why our attention is much on the reverse recovery time. The forward recovery time, it limits the rate of rise of the forward current and the switching speed, because we say the time is very small for the forward, and that is why the forward current rise is also limited with respect to that time, and also the switching speed is also limited because of that time. So from there, we have what we call the reverse recovery charge. We have seen the reverse recovery time, we have seen the reverse recovery current. Now we have the reverse recovery charge, which is QRR, and it is the total amount of charge carriers that will cross the junction of the diode when it is in reverse direction, due to what? The change of state from the forward conduction to the reverse blocking conduction. And as we all know, the charge is a product of what? Current and time. Therefore, the value of this reverse recovery current, if we want to determine it, we have to calculate the area from this cup, this area during the reverse conduction, from the zero crossing line to the point where it returned to this 25%. Okay, so if we want to calculate it, you say that the charge is equal to a half times the reverse recovery current times T1 plus a half IRR times T2. If we factorize a half IRR, we will be left with T1 plus T2, which is equal to our TRR. Therefore, our reverse recovery charge is equal to a half times IRR times TRR. So from here, we have seen the dynamic characteristic of a diode, and we also look at the effect of reverse biasing the diode by this reverse recovery analysis. Now, the diode is of different types. We have general purpose diode, we have high speed, that is fast recovery diode, and we have short key diodes, three of them. So the first one is the general purpose diode, and this diode, it has very high reverse recovery time, and the value of that high reverse recovery time is in the order of 25 microseconds. Somebody will be surprised. Microsecond, and you are calling it high. Yes, the high and low, they are relative terms. You have to compare them with something for you to know whether something is high or low. So we are going to see shortly that this 25 is high if we compare it with the other ones. And the reverse, the general purpose diode, they are used in low speed applications where the frequency has a maximum value of 1 kilohertz, and the current rating is from 1 amp to several 2000 amp maximum, and the voltage rating is from 50 volt to 5000 volts, that is 5 kilovolts. And these diodes, they are manufactured by the diffusion process. I mentioned three processes of manufacturing the diode, either alloying method, diffusion method, or epitaxial growth method. So this one is done using diffusion methods. But when you want to use the alloy methods, the diode that should be used for welding power supplies where we require a very large amount of current, instead of using the diffusion method, we use the alloying method, which is stronger. And of course, this type of diode, that they are the most cost effective, they are not expensive, they are very rugged. For them to be damaged is a big trouble. And their rating, the ones that are used using the alloying method, is up to 300 amperes, and they can conduct up to 1000 kilovolts, or 1000 volts rather. The second type of the power diode is what we call the fast recovery diode, and this one, it has a very low recovery time because it is 5 microseconds. So compared with 25, you see that, yes, then we can call that one high, and this one we can call it low. And the major area where this fast recovery diode is applied is in electrical conversion. That is when you want to change AC to DC or DC to AC in converter circuit that do this, then we use the fast recovery diode. And the current rating start from less than 1 ampere up to several or hundreds of amperes, and the voltage rating is from 50 volts to 3 kilovolt. And these fast recovery diodes, they are preferable whenever you are dealing with freewheeling SRC circuit. What do we mean by freewheeling components? Whenever you say a diode is freewheeling or a silicon control rectifier is a freewheeling, it means you use it in a circuit in order to protect a component from reverse current as a result of inductive loads. So whenever we use this fast recovery diode in this kind of applications, freewheeling applications, where we want to protect it from the reverse voltage damage. And the reason why it is used, it has low recovery loss, and it has lower junction temperature, and it has reduced rate of change of current with respect to time. So these properties make it suitable for these freewheeling applications. And if you want to use it for a very high rating greater than 400 volts, then you have to use the diffusion manufacturing process. And this the recovery time for this diode is controlled using either platinum or gold diffusion process. And for application that uses less than 400 volts, we use epitaxial growth methods, and they provide faster switching speeds than the diffusion one. And these epitaxial diodes, they have very narrow base, and this is the reason why they are faster, because their reverse recovery time is in the order of 50 nanoseconds. For you to change from micro to nano, you have to divide by 1000. Therefore, 50 nano is much smaller than the 5 second we have seen. Then the last one is what they call the Schottky diodes, and this is a diode that is made using the alloying method, because it has a metal which is typically aluminum, and it has another junction which is a semiconductor, typically N-type semiconductor. And the process here is that the Schottky diode, it has a larger barrier for electron to flow from the metal to the semiconductor. And whenever this Schottky diode is forward biased, you find that the free electrons on the inside, they will gain enough energy to flow, because the metal will assist in pushing them to flow faster because of the conductivity of the metal. And because the metal has only free electrons, it doesn't have holes, you find that we don't have any hole in the metal region, and therefore there is no charge storage, because it is only when you have the holes that you can store charge together with the electrons. But in the metal region, we don't have holes, therefore there is no charge storage. So this decreases our recovery time. Therefore, the Schottky diode can turn off faster than the ordinary PN junction diode because of this feature. And the Schottky diode has relatively low forward voltage drop, and it has low reverse recovery losses. Therefore, all these ones are advantages to it. Now, the leakage current is higher than in the PN junction diode, which is the disadvantage. And the maximum voltage it will be allowed for this Schottky diode is only 100 volts, and the current rating maximum is 300 amperes. And the Schottky diode are mostly used in low voltage application, because we can see it's limited to only 100. And of course, they can be used in high current application because they can conduct up to 300 amperes. And their frequency of operation is very high, from 100 kilohertz up to 300 kilohertz, and that is why it is very fast. And this Schottky diode, it has another name. It is called hot carrier diode. Now, this table gives us the comparison of the properties of these three types of power diodes. That is the general purpose, the fast recovery, and the Schottky. Here we have the rating, the range of their currents and their voltages, the reverse recovery times, and the turn-off time, and of course the voltages they conduct in the forwards bias, that is the drop voltage. Ladies and gentlemen, this is the end of the second lecture. Thank you very much. Till we meet in the third one, I advise you to watch and watch over again and ask any question when you have any problem with anything. Thank you.